So the next speaker is Anita Weidinger from Innsbruck, who's going to talk about error mitigation for quantum approximate optimization. Anita.
Thank you. Can you hear me now? Yeah, good.
So, yeah.
Thanks for the intro. Yeah, so I'm Anita from the University of Innsbruck, and yeah, I'm in the middle of my PhD, and I'm glad to have the opportunity here to present the work I do there. It's about error mitigation for quantum approximate optimization. So here you can see our group. We are dedicated to quantum optimization, and especially on how to solve them on actual hardware. So Glenn is also involved in this project. He just had the previous talk. Also the head of our group, my supervisor Wolfgang Lechner, you can also see in the middle. And there is Glenn. And yeah, I also got told to tell you that we are actually looking for PhDs and postdocs. So if you're interested, you can write Wolfgang, or you can ask me or Glenn if you have any questions. Yes, so here's the outline of my talk. First I will talk about some background, especially about the LZ model. We already heard it a bit in Glenn's talk, and it's basically also the heart of our group, as most people work on it. And then I will also tell you a bit more about QAOA. Then the new scheme, error mitigation QAOA, show you the results and the summary. So the motivation behind the LZ model is to actually how to encode optimization problem on a physical hardware. For example, we have this problem shown here, this graph. It has 9 qubits. It's a complete graph described by the Hamiltonian here on the left. And when you want to implement it, then you just have a 2D grid, and you also don't have all the connections you want to have to implement all your interactions. So that's a big challenge, and the main motivation behind the LZ model, which can implement these interactions as local fields. It was proposed in 2015 by Wolfgang Lechner, Philipp Hauke, and Peter Zoller. So that's also where these 3 letters come from the first letters of the authors. Yeah, but how does it work? I want to show you on this small example with 4 qubits. It's still with all-to-all connectivity. And yeah, the LZ model actually encodes the parity between 2 qubits. So if 2 qubits are parallel, so if they're both up or both down, they get the value 0. And if they are anti-parallel, they get the value 1 in the LZ model. And here I have 4 qubits with 6 interactions. So we'll have 6 qubits in the LZ model, which can be arranged in this triangle form. And the interactions are now these local fields. And you can also see now that I have these gray triangles and this gray diamond that are actually the constraints. And I need them because I now have 6 qubits instead of 4. So there's configurations possible that do not translate back to the original problem. So for example, if I flip this top spin here, then now we will try to decode it back into this logical version. So I will start with the lowest qubit here on the left. It tells me that qubit 0 and qubit 1 should be parallel, so I can set them both to up. And then I look at the next qubit. It tells me that also qubit number 0 should be parallel to qubit 2 should be parallel to qubit 0, so I can set it also to up. And the top qubit now tells me that qubit 3 has to be anti-parallel, so I can set it to down. But then if I go on to the next qubit, it tells me that qubit number 1 and 3, they should be parallel. But in fact here they're also already anti-parallel, so they're up and the other one is down. So I can't get the corresponding logical state from this physical configuration. And as I can't just throw this state away and we're just interested in the ground state, I can get it an energy shift. And I do this with these constraints. So for example, this 4-body constraint has the condition that it has to have an even number of zeros, but here there are 3, so this constraint is violated. And yeah, it's just an odd number of zeros if you have a free body constraint. This is now explained for a complete graph. So if I add one more qubit here in the logical model, then it's just a full row here in the LZ model, so it scales up that easily, and it just has a quadratic qubit overhead. This is for complete graphs, and it can also be done for more general graphs, as you can see here. Here I have a three regular graphs with 6 qubits. It can be compiled to this parity version. And yeah, you can also see that this 4 qubit constraint is formed with this closed loop in the logical graph. And also this yellow constraint is denoted here by these yellow lines. I can also use it on hypergraphs, so if I have not only 2 body interaction but also here 3 body interactions, I can compile it to this parity encoding. And actually this compiler going from this logical graph to this parity graph is the core of the company Wolfgang founded about 2 to 3 years ago, Parity QC. And here I want to show you some pictures they have in their gallery. So you see always a logical graph and then the compiled graph next to it. And you maybe see that if there is kind of a symmetry in the logical graph, you can also see it in the parity encoding. So that was enough advertisement. It was originally proposed for quantum annealing, so there's a lot of research done for quantum annealing, but yeah, then it also got extended to digital quantum computing, QAOA, and recently now there are papers out for universal quantum computing. As I already said before, and you could have guessed from the title, I will talk now about QAOA. So QAOA stands for Quantum Approximate Optimization Algorithm, was proposed by 2014 by Dari. And yeah, here you see a very schematic scheme of how it works. So I will go quickly over it. We start with an initial state, which is in general equal superposition of all basis states. And then I apply my unitaries. So I have 2 unitaries. I can apply p times. So I have ux and up, my driver unitary, and the other one contains my problem Hamiltonian. And then I perform my measurements, and the outcome depends on this variational parameters, beta and gamma. So I will start with an initial guess, and then I measure it often enough to get an estimate of my energy. And then I hand this to a classical optimizer, which seeks to minimize this energy. And then the optimizer hands back a new set of parameters to the quantum circuit. And if I apply my unitaries, till I repeat it till I reach a convergence criteria, a certain amount of steps. If p goes to infinity, I get an exact solution. But actually in these devices, I would like to have a shallow circuit, so it also works good on shallow circuits, and which is the great advantage of QAOA. How does now QAOA work on the LHZ model? So here you see that I now have one more unitary, UZ and UC, and the UX is just similar as I had before with my driver term. And the unitary containing my problem Hamiltonian now gets split up in 2 parts, because my LHZ Hamiltonian contains the local field term and the constraint term. And actually the driver term and local field term, they are single qubit gates. But now the question is, how would I implement now these constraints? So here in the bottom you can see now a little bit of a bigger LHZ with more constraints, and for example a 4-body constraint plaquette can be implemented with this scheme. I make 3 C0 gates, a Z rotation, 3 C0 gate back, and this can be visualized with the line. So a line is a C0, and this square is the rotation. So if I now exchange the plaquences with these lines, it looks like this. And the colors here actually have a meaning, namely that the constraints with the same color, they can be executed at the same time, so I can parallelize this. If I now compare it with the original, with the Ising Hamiltonian, then we have to do some rerouting I want to explain here. So again, my mixer unitary is a single qubit gate, but what about the interactions? Especially if I have here all these wanted interactions I want to have, but I just have these few existing connections. I can implement an interaction easily between neighboring qubits now with 2 C0 gates in a rotation. And what about qubits that are not neighboring on this grid? I would have to swap them around with 3 C0 gates, so I can implement this. But C0 gates are quite expensive. And especially if you have a bigger problem with more qubits and a more different connectivity, then you need a smart scheme to implement it and to use as little swap gates as possible, especially if you do not necessarily need them. And there are different strategies, techniques, and we use here the compiler ticket from Cambridge Quantum Computing to optimize our circuit so we don't need too many swap gates. There was a paper actually from Parity QC. It's still on archive, but I guess it will be published soon. And it looked at the number of C0s that is needed if we encode a problem with the parity mapping or with the rerouting. Here's some results. They looked at different graphs with different combinations of k-body interactions, so not only like 2-body interactions. So on the x-axis here you can see the mean interaction order. On the y-axis it's the ratio between the number of C0 gates used for the parity encoding and for the rerouting. So if the value is 1, they both need the same amount. But if it's lower than 1, the parity mapping uses less C0 gates. You see it also for different system sizes. So it's we see that especially if the system size is higher and we use higher order interactions, the parity mapping has the advantage of needing fewer C0 gates. But of course there's always a drawback. Namely, I said before that we have this quadratic qubit overhead, and if we look at the number of basis states we have compared to the number of logical qubits, in QAOA I will have a high probability to measure such an invalid state, an unphysical state that will, which I can't decode back into a logical state, so it will never contribute to the solution. So of course that impacts the performance. But gladly we have a solution for this now. So here you see now our adapted QAOA. It's the same as before, but the new thing happens now here at the measurement, where we also will apply a decoder, and this decoder will convert a physical state into a logical one. So I will hand a logical energy to the optimizer. So my optimizer will always stay in this logical subspace while the circuit is done on a parity mapping. But how does this decoding work now? Because here in the start I had this example with this invalid or unphysical state, and we ran into this contradiction. But actually before we read out this qubit 1-3, we had all the logical qubits determined. And if we look now at these red edges, which correspond to these 3 qubits I read out here, then we see that they cover all the nodes, so all the qubits, without making a loop. As soon as we made the loop here, we ran into this contradiction. And actually, this definition is is actually the definition of a spanning tree. So if I choose now every spanning tree from a graph and use the corresponding physical qubits to decode, then I will actually always have a valid logical state. So here I have some examples, like the first row is like the qubits from the parity mapping I use for the decoding, and below you see the decoded state, and the arrows are the spanning tree. So in the first example, that's just the same as above. Basically, take one qubit as the base, here the qubit number 0, and then I look what's the alignment to all the other qubits. Are they supposed to be parallel or anti-parallel? And that's actually also the same in the second example. I just take a different qubit as a base. Here I have complete graphs, and they're in total n to the power n minus 2 spanning trees if I have n vertices. And if I have here now 4 qubits, I have in total 16. So here you can see the rest. The decoding maybe is a little bit more complicated. I take one qubit as a base, determine 2 others, and then I take another qubit as a base to determine the rest. But you will also see that not all the decoded states are the same. So if we go back to the big example here, like the 2 in the middle, they're all spin up, but the outer 2 ones, they have somewhere spin down. And that's the case because I decoded an unphysical state. So they can give me different logical state for every different spanning tree. If I would have a physical state, for example, this one here would be 0, then I would have this constraint would be fulfilled. And then every tree would give me the same logical state. In that case, they would all be up. With this information, I can now create a new objective function for our classical optimizer. So, for example, I have this physical state. Then I can just take qubits that correspond to a spanning tree in the logical model, for example, this one, and then I can construct my logical state from it. And I don't just have to take one, I can also take several ones, for example, M trees. In the small example on the bottom, it would just be a second one. Then I have 2 logical states, and then I take the average energy to be my new objective function for the optimizer. Here you can see the results if I use a random number of spanning trees. So I have different system sizes. Take random spanning trees for p equals 1. So I apply the unitaries just once in my QAOA. And here you see on the y-axis the success probability. So success probability of 1 means that I measure always the ground state. What you see is that already if I take just one spanning tree, I get a decent success probability, but the error bars are really big. Here I have 100 random instances, that's the median, and the error bars are the 25th and the 75th percentile. So it really depends on the problem which spanning tree I take, so the outcome is random, but luckily that decreases the more spanning trees I take. Also, the more I take, the better the success rate. If I look now at, if I fix now my qubit number to 6 qubits, here we see how it performs for different depths, so p equals 1 and p equals 2, applying the unitaries once or twice. And we see a similar behavior. But now I want to compare it to the rerouting method, like the logical qubits versus the physical. And here I see that, I have quite a qubit overhead, so what's actually then a fair comparison between those two? And here we want to fix the qubit number. So I will adapt the success probability for the rerouting with this formula. So in this example, because here I have 15 qubits and here I have 6, that means I could execute the rerouting 2.5 times. Also, I want to fix now the spanning trees. So I take a fixed set, which are the logical lines. So the number of spanning trees are the number of logical qubits. So the logical lines, we already saw them. Like this, for example, is logical line number 0, and I actually contains all the qubits which have a 0 in it. So basically here I fix qubit number 0 to up or down, and then I can determine how are all the other qubits aligned to it. So in that manner I can also have line number 1, 2, 3, 4, and 5. And like this we have an equal distribution of my trees, so every qubit is involved in the decoding. So that are the results. Again, still on a DL circuit with no noise. The success rate for the rerouting is adapted with this formula, and I show you the results for p equals 1 and 2 for different system sizes. So for really small system sizes, I have a high success rate, and it lowers down the bigger the system gets. And maybe here it decreases less strong than in the parity QAOA. But here I also want to reconnect to the previous result. So if we look at this point, which is like 7 qubits, 7 trees, that's exactly what we have here. So we could use more trees to improve it. So that's still an open question, how many trees you want to take for the decoding. In a complete graph, you have an exponential amount, but that's maybe not the overhead you want to have. To address the question we had in the first talk, it's concerning the number of parameters. For the rerouting, we have here like 2 parameters and here 4. And for the LZ, we have 1 more, so this would be with 3 parameters and this with 6. So I guess it could also make sense to apply 1 more layer for the rerouting to also have 6 parameters here. But yeah, I don't have them here now. Now we finally apply the noise, the depolarizing noise, on our 2 qubit gates. Just to remember, for the rerouting, we needed the swap gates to implement all the interactions. And in the LZ, they come in with the constraints. And also, I still apply my success rate for the rerouting with this. And yes, here the rerouting needs less CNOT gates. And nevertheless, we see that with the parity QAOA, I have a higher success rate for all the error rates I show here. And yeah, and here with 3% about, it's as good as the rerouting with known noise. Yeah, with this.
So this is local depolarizing or global?
Yes.
Okay.
I also have error rate on my.
Like a single layer of depolarizing?
Like every CNOT gate has a specific error rate.
Okay.
There's also a fixed error on my 1 qubit gates, which is just 0.1%. Okay. Oops. So now to end now. So I showed you how to adapt the new objective function based on the spanning trees. And also want to note here that, yeah, you can apply it to more general graphs. You just need to find a spanning tree on the logical graph. And the success rate for this parity QAOA was always higher than for the QAOA with rerouting, with and without noise for the studied system sizes, even though I needed fewer CNOTs in that case. And as this others results showed, the disadvantage may disappear for higher system sizes and high interaction terms. Nevertheless, I also want to say that these compilers we use, they're always improving. So you should also try to improve the number of CNOT gates you use on the parity mapping. Yeah, and some open question is what's the number of needed spanning trees, especially if I go to bigger system sizes, and maybe it also makes sense to adapt the objective function. Here we took the mean. Maybe it could be useful to take the minimum. Yeah. Thank you for your attention. Looking forward to questions.
Thank you, Anita. Indeed. Okay. Let's deal with this one. Good. Who would like Dennis.
Yeah, thank you. So in the beginning you showed the quantum annealing, QAOA, and universal quantum computation with the LHZ. Then you said that QAOA, so it needs another unitary, right?
Yes.
I was wondering, does that come from the, so you said you did quantum annealing first, does that come from the trotterization that you then have 3 parts in whole?
No, it was on this paper. They just looked if I would separate those 2 terms, it would have a better performance. And that's the only reason. You could put them together, but then you have just one parameter, but then maybe it's not as good.
Ah, okay, so it's for practical reasons then.
Yes, exactly.
Okay. Yeah, thank you.
Juanjo, yes, sorry. Thanks.
Okay, oh, good. I have 2 questions. One is the way you normalize the success probability looks a little bit weird to me, because you write PGS equals to the power of the error probability.
No, that's more the number of physical qubits by the...
Yes, but 1 minus PGS is the error probability. So I would expect that PGS star would be 1 minus that number.
1 minus?
Minus that number. So the one the number in the parameter
yes,
in the parentheses is the error probability.
Okay, yeah.
Okay. And another question is that, I mean, this encoding considers all possible couplings between qubits. If you have particular the encoding, the H sets encoding considers all possible couplings or all possible IJ terms, no? Can you do better by just, if you have a particular Hamiltonian, dropping some qubits from your parity encoding?
You mean if I don't have a complete graph, so if I don't have this?
You have you know your graph of the problem you want to simulate,
yeah.
but instead of having the full triangle, you could just keep the ones that really have interactions in them.
Yeah, but don't know if you would simulate the full problem then.
I mean, if you have a graph that connects the qubits with each other, and no qubit is isolated, just knowing the parity between pairs of qubits gives you the full assignment to the spins, right? Do you need them all? Do you need all pairs to know the state of the qubits? Yeah. I mean, in the end, you have your spanning trees allow you to give an assignment to the qubits. So what I was wondering is that it also tells you that you have more qubits than you need.
You mean if I just take one spanning tree, I could just simulate?
Yeah, or a subset of them and have a smaller model on the parity space.
I'm not sure if, because here I have then all interactions, and I know, for example, how qubit 0 and 3, I have the interaction. If I would drop that here because I don't need it, it's
but in this case your matrix J is full, but I was thinking if you have a particular model,
for example, like
if you only have like a square lattice, not diagonal interactions, can you simplify the model on the right?
for example, if I have a like
Okay.
something like this.
So in the end, the model on the right only has the non-zero elements of the matrix
Yes.
J. Okay,
Yeah.
fine. That's what I wanted to understand. Sorry, I didn't get it.
Any other questions? Time for questions. So maybe I'll ask a question, and this is, I guess, a kind of high-level question, and maybe there's no obvious answer to this question. So the LHZ has now been applied to annealing and QAOA, and you also mentioned briefly universal gate-based quantum computation. So is there any indication which of these 3 it's most powerful for? I mean, if you know, does it lend itself particularly to the annealing approach or not? Or how does the 3 compare, I guess? Yeah,
I mean, with QAOA you have the advantage that like you can use shallow depths, so it may be more useful in a near term and have these NISQ devices. And anyway, universal quantum computing is always very nice, but that's still far away, right?
So I guess my question is not quite as general as that. but you know, in terms of the advantages provided by the parity encoding, is that, you know, does it gives you a really big advantage with one of these approaches and only a slight advantage with the others, or is that not clear yet?
Do you know, Glenn?
So I can answer like this, I guess.
Let me. Let me give you the microphone.
So I can maybe we can say that for the case of quantum annealing, it's a bit harder to deal with this increased space, because we usually have to deal with longer times, while with these circuits that can be optimized variationally, you can have shorter times, and these approaches that we described to these corrections that actually exploit this overparameterization of the LZ work better in this case. So in this kind of cases, it's quite promising. And there are quite some work even in the universal setup, which try to use this overparameterization to gain advantage. So wherever this can be used is more promising. And in annealing, we are still trying to work out how to make this work properly.
Any other questions for Anita or for Glenn? If not, let's thank Anita again. Thank you, Anita. Let's move on to the next presentation. Gemma. Excellent, excellent planning.
Yeah, we'll see how it goes.
Is that yours? Or?
It's mine.
Yeah. Thanks, Lisa.
Okay, and
All set?
I think so.
Good,
Yeah.
excellent. Right, so the next presentation is Gemma Bennett from the University of Durham. We'll be talking about using copies to improve precision in continuous time quantum computation. Over to you, Gemma.
Hi, yep, thank you very much for inviting me to talk. And yeah, today I'm going to talk to you about a technique that we've developed that uses copies in order to improve precision in continuous time quantum computing. But the first thing to mention is that if I do a bad job of explaining it today, or you just want more details, then there is a paper available on the archive at this link here for extra details. Okay, so I'm going to tell you about how our technique for improving precision works today. But first, before I tell you how it works, I need to tell you why we need to improve precision for continuous time quantum computing. So, as theorists, we want to solve optimization problems on our quantum computers, and these come in all sorts of shapes and sizes. But the main thing about these problems is that the solution is the lowest energy state of these particular problems. We like to represent our optimization problems on Ising models. Here is a very simplistic Ising model. Yeah, you can see my pointer, that's good. Just 2 qubits. Each of these qubits have a field applied to them, H0 and H1, and it's connected by coupling strength J01. If we want to know about the energy levels of this Ising model, then we can look at its Hamiltonian, which will look something like this. So if we want to represent an optimization problem on this Ising model, the thing is, as we want to represent more and more complicated optimization problems, we increase the number of terms that we need in our Ising model, and also the fields and couplings that we want to have on our Ising model become more and more complicated. So you could end up with fields that look more like this. And this, unfortunately, is where reality may have to step in, because when we try and set our optimization problem on a real-life quantum computer, we become limited by the fields and couplings that we're able to set on our quantum computer, such that if we're trying to represent this more complicated number here, what we may actually end up setting is something more like this. And the problem with that is that you're shifting around the energy levels in your Hamiltonian, such that when you come and find the ground state, or the answer to your optimization problem, you end up finding completely the wrong answer than the one that you were looking for. So how do we go about stopping finding the wrong answer? Well, a naive approach might be that if you try and find the ground state the first time and get the wrong answer, you could just simply try again, and you might be lucky the second time and get the right answer. But we actually want to do better than this. So building on and making several differences to a technique called QAC, we start off by connecting several copies of an Ising model together. We then subject each of these Ising model copies to a lack of resolution. So a lack of resolution on the fields and the couplings in our Ising model. And we define this lack of resolution as a number of allowed values between -1 and +1, which itself is defined by 2 to the p + 1, where p is the precision. And we vary this p from 1 to 10. So here's an example here, where we have low precision, and you see there's a low number of values between -1 and +1 that we are able to set. So this means that the problem that we're able to set on our quantum computer is not going to be very close to the one that we want to set for our optimization problem. But as you can see, as we increase the precision, there are more allowed values between -1 and +1, and this means that we are getting closer to, so we're able to set our h's and j's closer to the ideal values that we need for our optimization problem. We then measure, once we have subjected our Ising model copies to a lack of resolution, we then measure something we define as fraction correct. That is, once subjected to a lack of precision, the fraction of times we still find the correct ground state of our Ising model. A key subtlety to our technique is that we only require one or more of these Ising models have the correct ground state for us to consider this run a success. We then have tested our models on several different examples. So here we have 2 or 3 copies of spin glasses and spin chains. And what we wanted to find is what is the optimal strength of length between copies that we needed in order to maximize the fraction correct. And what we find is this. So here we have our different examples again, 2 copies and 3 copies, and what we've measured is fraction correct versus the strength of the couplings between the copies. And here we see that we have varied the inter-copy couplings between -1 and +1. So here are ferromagnetic links, and here are anti-ferromagnetic links. And the 2 colors represent a p = 3 and a p = 4, so a lower precision and a higher precision. And these dotted vertical lines are representing the allowed values between -1 and +1 that we are able to set for our couplings between the copies. And what we see is that in these cases, that there's an optimal value of JF where the fraction correct is maximized. So this is the ideal strength of coupling that we want to set in between our copies. Another interesting thing to note is that for 2 copies, we do have this maximum in fraction correct, but the improvement tails off quite quickly as you increase the strength of your antiferromagnetic links. On the other hand, for 3 copies, we don't see this tail off as much. So this.
What was the yellow and the blue data?
So the yellow data is for p = 4, and the blue data is for p = 3. So you might just be able to see the yellow is probably not very clear in this, but the sort of vertical dotted lines represent the allowed values of yellow, and then the blue ones correspond to the allowed values of PO3. Okay. So what we've seen there is that 3 copies is better than 2 copies. So we want to know why is that, but also we want to know why does it work in the first place. And the answer to that question is energy penalties. And so what we have here, instead of just having a single optimization problem, it's 2 optimization problems connected together, but antiferromagnetically. So the optimization problem wants to be in its preferred ground state, but the links in between them are working against them. So you see that if we have 2 copies that are exactly the same, then this receives the highest energy penalty. The more states we flip compared to the original copy, the lower this energy penalty becomes, until we see that if we have a completely flipped ground state compared to the first ground state of copy A, then we see that we actually receive the largest energy benefit from being in this situation. But it's more likely that this state is going to have a much higher energy because it's not the optimal state for your optimization problem. Another way of looking at this is something like this. And what I've plotted here is the energy levels versus the possible states of our 5-qubit Ising model. So a little bit confusingly, I admit that I've changed out the 5-qubit bit strings to decimal numbers, but don't worry too much about that because I'll just explain it now. So what I've drawn here is the energy levels for a p equals 3 problem. And what we can see by these dots is that, so in this orange dot here is the ground state of the original problem with true precision. And what we see is that this is actually higher than this dot here, which is the ground state at p equals 3, which means that this example is broken by the lack of precision. And I've drawn in some arrows here. And what these arrows represent is the energy boost or downshift, which is given by connecting the initial copy with the second copy of, together. So if we look at the ground state here, we see that there's a large energy penalty or boost, because this is what representing what would be the case if I just connect 2 copies of the same two of the same copies together. On the other hand, we see that if we connect a completely flipped copy to the original copy, we see that it has a large downshift, but this is nowhere near enough to overtake the 2 copies that are the same. So this is also not optimal. But what we do see is that there is another low-lying state which is almost completely flipped, but is low enough that it overtakes this incorrect ground state and connects with the true ground state rather than the incorrect ground state. So, sorry, that explanation may have been a little bit confusing, but what I'm trying to say is that, so we started off with the original ground state when there was no errors subjected to it. By subjecting a lack of resolution, we then had this shifted to a different ground state, so it was broken. And then by connecting these 2 copies together, we're able to recover the true ground state along with almost fully flipped connector state, because this just, so you can think of it as, now we're not just trying to solve the optimization problem, but kind of coming to a compromise between the optimization problem and the antiferromagnetic, satisfying the antiferromagnetic links, which is what we think is providing us this improvement from connecting these copies together. So now we thought about 2 copies connected together. Why is 3 copies better than 2 copies? Well, at first you might think, well, there's 3 copies, so there's going to be a larger energy penalty to having them all in the same ground state. Well, this is true. But what we see is that when we flip a bit compared to of one of the other states, we see that this energy penalty reduces. But then when we flip another bit, the energy penalty stays the same. So for the antiferromagnetic links, these two different ground states are energetically kind of not preferred. And we find that, in fact, if we connect all three copies together, we only get an energy benefit of -5, so not as strong as the energy penalty you can get by connecting all three of the same together. But the interesting part is that the frustrated link that you need in 3 copies, it does not necessarily have to be in the same place between all these 3 copies. So in order to maximize the energy benefit, you do not have to have a completely flipped antiferromagnetic state. So it's almost more likely to be a state that is closer to the correct ground state. And this is why we think we do not see the tail off as strongly for the 3 connected copies. Okay, now I've tried to explain a bit about behind why it works. I'll go on to some more concrete results that we've got. So what we decided to test is Ising spin glasses, because they're NP hard and also uniformly hard, and they've been studied in the continuous time setting in this paper here. And we connected 3 of these copies together in this loop or triangular configuration. And we also set these links to be optimal, so the minimum allowed antiferromagnetic links, as seen in this graph here. And then we measured the fraction correct, remembering that we only need more of these copies to be correct for us to consider it a success. We then measured this against the fraction correct of just having single copies on their own, and for different values of p, so the p going from 1 to 10. We could also measure a breakdown of the fraction correct, so fraction of time there are 3 copies correct, 2 copies correct, or just 1 copy correct. And then we could plot this versus the precision, and on the left-hand bars you see the results from a single copy. So you can see that as the precision increases, the fraction correct also increases. This is what we would expect. As the precision is increasing, we're getting closer to the optimization problem that we'd ideally want to represent. But interestingly for us, these right-hand bars are the results from 3 connected copies. And what we see is that there is an improvement or an increase in fraction correct from just a single copy to 3 connected copies. And interestingly, this is not caused by just having 3 copies correct, but by having 2 or just 1 copy correct out of the 3. We also wanted to measure the effect that our technique had on instances by themselves. So the fraction of times our technique had no effect on the ground state, the fraction of times it had a positive effect, so we recovered the ground state from a broken instance, and then the fraction of times it had a negative effect, so the fraction of times an instance's ground state was broken by using our technique. And what we found is that for the majority of instances that it doesn't have any effect, but positively for us, there is this small bar here that indicates that there is a proportion of instances that are corrected by using this technique. And also good for us, there is only a very small situation where instances are broken by using this technique. And if you really wanted to get this tiny improvement from using that we lose from using the 3 connected copies, you could ideally have an external individual copy on its own, such that you could account for when this was happening. So if you can see that these are examples, these are just examples from 5 copies, and if I just replace the graph to look like this is the same graph, but instead with lines and dots, and the solid line is for the 3 copies, and the dotted, other way, is it the other way? Yeah, the other way around, yeah. Solid lines for single copies, and dotted line is for the 3 connected copies. And so we repeated this for 5, 7, 8, and 9 qubit spin glasses, and the gap between the solid line and the dotted line indicates that the improvement continues for larger sizes, which is good for us. And we also wanted to measure the gain in bits of precision that we were getting, or the relative gain in bits of precision that we were getting from using just a single copy to using 3 copies. So what we did is we instead flipped the graph around to measure the fraction incorrect, and plotted an exponential fit to the single copies, and then used the measured horizontally from the 3 copies, the fraction incorrect for the 3 copies, to measure the relative increase in precision we were gaining from using 3 copies. And what we found is a graph like this, which indicates that as precision increases, precision improvement increases a little bit, and we find that around p equals 7, we're getting roughly 3 bits of improvement. We also wanted to check how, so up until now we've just been looking at instantaneous ground state, so just finding the ground state classically, but we also, and this could be seen as the same as just doing a perfect like adiabatic evolution to find the ground state. But what we wanted to see is whether this works with other types of continuous time techniques. So we chose quantum walks. And the key thing about these is that you don't necessarily get the answer with probability 1, and that it accesses excited states along the way to finding the ground state. And so it looks something like this. So here we have the target or problem Hamiltonian. It's just our spin glasses that we had before. And we have the driver Hamiltonian, which looks like this. And a key thing that we wanted to check was gamma, because for quantum walks there is an optimal gamma where the success probability is maximized. And these were previously found in this paper here. And we wanted to, for just single copies, we wanted to check the effect that our technique was having on these optimal gammas, because if this changed a lot, it could potentially indicate that our technique was having a negative effect on the success probability of the quantum walk. And so yes, so then we wanted to compare the single copies with true precision, single copies with precision equals 3, so an error added to them, and then the 3 connected copies with the lack of precision as well. And we tested this for 4 instances, just to get an idea of what was happening. And what we found is this. And so the green lines represent the single copy true precision, orange lines single copies with p equals 3, and then the blue line is the 3 connected copies with p equals 3. And what you see is various things are happening, but that's okay, because actually this is an average effect. But the key thing to us is that the optimal gamma does not seem to change much, so that we would be able to use a similar gamma when we were using quantum walks. Okay, and that's all I have for now. In conclusion, what we found that by connecting 3 copies with minimum strength antiferromagnetic links makes our problem more robust to a lack of precision. And this could be used to increase the effective precision of the optimization problem. And if you want more information, there's the link to the paper again. And thank you all. Also, thank you for my collaborators, and also thank you all for listening. And yeah.
Okay, we have time for questions. Let me grab the mic. Hello.
Do you know how robust is your system for lack of precision in JF?
So at the moment what we've done is just the JF that is, so JF was subjected to precision, but only the same precision as the rest of the copies. So which, yeah, if you're, it kind of makes sense, because that's almost, if you're setting it at like the minimum precision that's available. So
Yeah, like
Yeah.
also this is kind of related in the sense that if you increase the length of your chain and you have some not necessarily precise setup, then you can have different JFs on different links of the chain. And like, how does this affect the setup?
I am not sure about that because, yes, so yes, so we have only tested the links being the same, so we don't necessarily know as much, but yes, you could expect that potentially if you're just connecting two copies together, it would be quite sensitive to changes in the JFs. Also, there's kind of, it seems like in some situations it's better to leave, because this is an average effect, in some situations it's better to leave copies disconnected or even certain qubits disconnected, and that seems to give a better success probability, but it's hard to know without solving the problem completely, it's hard to know when you should connect the copies or leave them disconnected. So that's an open question still.
Okay, thanks.
Well, there's a little bit more you can say from that graph because the width of the...
Viv, do you want to take the mic?
Sorry.
Cheers.
The width of the peak, or if you look at that graph, the orange and the blue, the width of the peak it's not a sharp peak, so it's not only that minimum JF does it. You've got a little bit of leeway there. So can you see what I mean on the graph? It's not super sensitive to being exactly the minimum precision. You could, if it was twice that, you'd still have a pretty good effect.
Yeah, but this is still for the same value over entire chain. Yeah, and you could have like one part slightly on the right, the other part slightly on the left, and this doesn't mean that it averages to the same precision. Like I understand that this is like an open problem that you haven't investigated, but it'd be nice also to see.
Yeah, well, you're talking about having very different available precisions in the setting in the hardware. I'm not quite sure where the difference is coming from.
Like, from, let's say, hardware perspective, we can assume that we will never have infinite precision, yeah? So setting up all JFs equal to a given value is impossible, and some sort of fluctuations will be present there, and one fluctuation can drive us to the plus, the other to the negative side, and like, here you assume
Oh,
that
I see. You
everything
just,
is
well,
the same.
Gemma didn't go into this for time, but to avoid degeneracy in the small samples that we're using, we actually did put fluctuations on all of the values. So we have, I think, essentially tested what you've done, because if you try to do it exactly, your results get very skewed by degenerate ground states. So I think for practical numerical reasons, we have in fact covered what you're asking. But yeah, that was going to be confusing to explain that on top of everything else.
Glenn. Going in the wrong direction, sorry.
Okay, thank you for the talk. And I was wondering, like, these precision errors that you discuss are precision errors on the final Hamiltonian, just on this, how you're setting the parameter.
Yes, it's like the target, the precision
On
error
the target Hamiltonian, on the target Hamiltonian. Because like in the Grover problem, I think Anita and the collaborators, they checked that these precision errors indeed like wash out the Grover speed up, but they also looked at these errors which were just on the schedule, not necessarily just on the final, but like a perturbation of the schedule. Would your approach help also for these kind of errors, or not? Or do you have to change it? Or is it just for the error on the final, on the target Hamiltonian?
So that's what we checked. We haven't done any errors on like the driver Hamiltonian, if that's what you mean.
Yeah.
So we haven't done that. We just put errors on the target Hamiltonian.
Okay, I see.
Sagato, is this a question? It's a question for Sagato.
Yeah, so very interesting work. Yeah. So I was just wondering, in this same picture here, so you told these frustrations help you in the 3 case, but what if you took unfrustrated, like you took 3 copies, but couple like nearest neighbors? What happens? So see if the 3rd copy was just below, right, without a frustration.
Oh, okay.
Yeah.
So this is, I've done this, and it's similar to what happens with the 2 copies.
I see.
Yeah.
I see. And another question is that do you when you couple copies, you're kind of making the energy more the energy more lower of the 3 copies. So do you have to kind of fight it with like a more gamma, or does the time to reach the optimal also increase? When
Not that I have seen, like, not really done cumulative effects of the
right.
quantum walks. Yeah,
Right.
just looking at individual instances. So
Okay,
the gamma looks similar.
Similar. Okay.
Yeah.
Okay. Thank you.
Dennis.
Thanks. Could you go to the, I think it was a slide at the very end where you showed the performance with quantum walks for the
Okay.
3
Yep.
connected copies? So right. So what I would typically expect is something like in panel B, right, where the it becomes worse if you have the precision 3, and it becomes a bit better again if you have then the connected copies. But okay, on the left it's like worse, right? So
Yeah.
you said it's an average effect. What does it mean in this context?
So, well, even in instantaneous time, we find that although it is a small effect, that in some cases by connecting the 3 copies together, we lose the ground state. So the ground state becomes no longer correct. So that's what I was referring to by we only see an improvement when we take the average of all of the instances. So yeah.
There's another effect, which
With quantum walks as well is slightly different. Yeah.
somehow I always end up with a project that looks conceptually simple to describe what you're doing, and then the subtleties turn into 20 pages. Sugata knows all about this. It was true for this paper. But so if you just think adiabatic, you're only thinking about the ground state, right? And that's the only probability for that state is the only thing you need to worry about. When you run a quantum walk and you measure, most of the time you'll measure an excited state because it populates many different states. So now your criterion for success is different. It's what's the probability of measuring a copy with a correct ground state, including the incited state probabilities, so that actually everything has changed in terms of the probabilities you're summing here compared to what you would do for the adiabatic case. So that we're still looking into. But, I mean, this we just honestly said, like, all possible combinations can occur. But statistically, it's a little trickier to look at both how it changes, because excited states are now valuable. They're irrelevant for adiabatic. And, then to work out where they're valuable, because in any case, those excited states also help you with the single copies, and at some level, right? You have a good some probability of measuring the right answer, even when you've broken the ground state. So that's the subtlety there, that it takes a lot more working out that we haven't done completely at this point. And but we're interested in it to know how quantum walks are working to solve problems. There's a lot of stuff behind that. So. Yeah.
Okay, any more questions for Gemma? If not, let's thank Gemma again. Very nice talk. Thank you. And we'll now take a lunch break. So let's gather for lunch back in here at 2:15, please. The most interesting thing is the J equals 0 case, in my humble opinion. Object copy has done a pretty good job, which stands to reason. But you do see some improvement when you choose J. I thought Philip's got a fair question. Sounds like it's a question of digging the data out and just taking a look at it. Good.
Did you have any data or any problems without single bias fields?
Okay, right. Okay,
So you mean?
Something with the Z2 symmetry. Because I suppose like
Natasha,
simulations are all closed. Besides
Journal
the
physics. You checked in
Yeah,
there.
I had for a little bit now. I checked in and it had gone from Weidinger reports to like a waiting decision, and then it went back to a waiting referee reports.
That's odd.
So
As if they lost the referee report.
yeah, or like I don't know, wanted something clarified maybe. I don't know. Yeah, it was very
We need to
strange.
generate
I'll check it again today.
Oh, is it existing?
Yes, it is indeed the case. So
I think
I managed to get some
if
charge.
you like need to write down like, I don't think I fully understand what you're trying to say.
And this has like some Z2 symmetry. Right, we can flip everything, nothing changes.
Yes. Okay.
Now, you have 3 copies, and now you're introducing something which has something just pagized.
So you're talking about a Hamiltonian where there were no H's.
Yeah, so,
I have done this.
okay,
And it doesn't work. So
Okay.
you don't see an improvement.
Don't see an
It
improvement.
does rely on the H's, the asymmetry of the problem.
right, got it. Thank you.
Sorry, it brings a bit paranoia.
No, no worries.
You're in post-talk frizzle mode. That's a good place to be.
Jumped on you.
Maybe you can't solve it without so you have to think really hard to what the success criteria was. And you put two copies together, excited states and
Yeah, right. I can imagine. But I didn't catch this point actually when I mean before you said it. That there's this fundamental subtlety in the quantum models.
So poor generals are most of us under lockdown, we're just trying to get our heads around this complicated
Trying to
results.
explain it to each other
Yeah,
and
yeah.
Zoom as well.
Over Zoom results.
But that was a great talk. It was really easy to follow. So
Thank you.
That's the aim as well. Also, it helps me to understand it as well.
yeah.
The whole stuff with the energy levels is completely working out what's going on there. As I've been going, we have to try quantum walks, right? How do we decide whether it's worked with a quantum walk? What probabilities are there out? How do you combine the 3 of them, separate ones versus the ones together? And so the success probability, the fraction correct is different in the 2 cases. But that involves a lot of quite expensive simulations because you have that, you have to calculate all of those probabilities. You can't just analyse the problem Hamiltonian alone. You have to get the infinite. You can do it off the infinite time averages, so you can do it from the diagonalising before Hamiltonian with the gamma and that. But that's quite expensive.
Right.
Compared to just running a branch and down on the classical.
But then you need all the states or only like ground state and a few of the decided states.
You just need, so there may be a better way to do this, but it's not, we haven't been using it. You just need the subset of states that have 1 or more correct copies in. And even for the relatively small ones, that's still like, that's still a few thousand states actually,
Yeah.
if you've got to sum the probabilities for.
Right. okay, if you know which states you need, then in principle, like Lankosh algorithm or something like that would probably be able to give you.
Some talking should happen here, yeah. No, because we've been using the tools that Adam developed for doing the single copies and then applying them to 3 copies because we just had them, right? And that got us the first step. But now, basically running, but you see your smallest size you're running is 15 qubits.
Ah, yeah, okay, I see.
Yeah, because you've got to run the 3 copies.
And how large does it get?
Well, as large as we can, yeah, yes, we've got computational powerful, but I mean 9, so 9 we could do for, but that's just, I mean you could do larger for just the problem Hamiltonian, because that's 27. But as soon as you put the driver on as well, and then need to get out a subset, but that is still thousands of the excited states which you need the probability for.
Right.
That becomes a whole different computational task, and so as I said, yeah, I don't know how. See, essentially, even doing 15 was larger than Adam was doing by that method because he did 13, and then he switched method for the up to 20 qubits from his original work. So the fact you even got anything, that's why it's individual copies.
Yeah.
And then we started trying to do some of the averaging, but we need a better method. But I think it's a bit in the balance because you need, I mean, you know which states have correct copies, and that's just numbers. But
right.
because that's just patterns of zeros and ones. So you put one third of the qubits are in any of the 3 positions, then have to be a correct copy. And the others can be anything, right? So you can see it's a really large number that we've got to sum over.
Right.
So, it might be only a fraction of the exponential number, but it's still pretty,
So about the Lankosh algorithm that I said, so I didn't do this myself, I have one in the group, written Anita, I had references on the paper. I think, so the hard limits, which is probably right.
Wander down in the direction
Right.
of food.
So the hard limit is 42 qubits.
Yeah.